We're going to begin talking about scores now. So what's a score? Well, traditionally, when you put notes on paper like this, that's a score. Scores describe sound events organized in time. And we want to think about what is the corresponding thing to a score in a programming language or in Nyquist. And to get started, we need to work on some terminology. So first of all, let's talk about pitch. I put a lot of words on this slide. You can stop and read the slide if you want. I think I'm going to try to just demonstrate some of this rather than go through the text. Okay, so pitch in Nyquist is indicated by integers. So let's start out by saying play pluck, our old friend, 60. Okay, so we hear a sound. 60 turns out to be the pitch middle C. 60 is chosen because the same number is used in MIDI. And if we increase that by 1, let's edit this to 61, then you hear that the pitch goes up. It gets higher. It gets higher by musically what we call a half step. On a piano keyboard, it would be the very next key, in this case going from the white key, middle C, up to the black key, C sharp. In Nyquist, we call these steps. We could call them half steps, and maybe that would be more correct, but it's awkward. So we talk about steps in Nyquist. So for example, there's a function called step to hertz, and if we type in step to hertz of 60, we can see down below the answer is 261.626. That is the frequency in cycles per second corresponding to the pitch middle C, or 60, step 60. And for psychologists, I know I'm being very sloppy with the term pitch, and we'll talk later in the course about perception and what pitch really means. I'm using it in the informal musician sense. Okay, so let's play some more pitches. We'll go back and do pluck 60 for reference, and now let's go up by 12. Okay, that interval that you just heard, that relationship is called an octave. It represents a factor of 2 in frequency, and so 12 steps corresponds to a doubling of frequency. Now, to make things a little simpler, sometimes Nyquist has variables that are predefined to pitch names. So for example, I could have just said play pluck of C4, C4 being the variable for middle C. Okay, the C obviously is the pitch name in common practice music, and the 4 is an octave number, so if I change that to C5, we'd go up an octave. Great. All right, and we have other modifications to these variable names. Let's play pluck A4. Okay, that's an A. So we can also say AF for flat. So this is an A flat 4. And we can modify that with adding an S, AS4. That'll be an A sharp. And as you might already know, A sharp 4 is equivalent to B flat 4. So we could also write BF 4. And we get, in the Nyquist case, we get exactly the same same value, the same pitch. Okay, so you can use these common practice names like A, B, C, D. For pitch names, you can add S or F for sharp and flat, and for most of these names, and the integer at the end is the octave number. The next thing I'd like to talk about is the notion of harmonics. So again, there's a lot of text here, and you can stop and read it, but I'm going to try to present the concepts through demonstration. First of all, let me copy this expression and paste it up here just to be really clear what we're doing. I'm going to enter this command, which is exec splot of an oscillator expression. And what splot does, as you can see, is it plots signals in this plot window that Nyquist has. Now, what I just plotted was a call to OSC, the unit generator, but I've previously, in fact, this is from a previous lecture, we built a waveform and stored it in this global variable star table star. That's the default waveform used by OSC. And so, while we talked about these four harmonics, we never actually looked at what was stored inside the wavetable. So now you can see that it's this function that looks kind of like a ramp, or you might describe this as a triangle. Anyway, this is the sum of these four sinusoids stored in the table and repeated to generate this output. So this is running at the pitch C5, an octave above middle C, and we could play that. So let's just type play here. Oh, and that was very short. Let's fix the duration. We could do the same thing with a sine table. Let's listen to that. Okay, so you hear the same pitch, the same height of the sound, but the quality of the sound is much different. And we can, in fact, plot that thing that we just heard. I'll just use Command U to execute this thing right from the editor window. And so you see the same number of periods in the plot, but the shape is this very smooth sinusoid curve. Okay, so what can we learn from this? First of all, the repetition rate is the thing that determines the pitch height, the pitch of the sound that you perceive. Second thing is that you can change the quality of the sound by adding harmonics to the sound. So what's a harmonic? A harmonic is a multiple of this fundamental frequency, an integer multiple of this fundamental frequency. And that's what the wavetable was doing, is adding harmonics together. Now, it turns out that if you have a periodic signal, in other words, an exactly repeating signal, then mathematically, regardless of what that signal looks like, it must be the sum of harmonics, which are multiples of the fundamental frequency or the repetition rate. So it follows from that, if you want to build a signal with a strong sense of pitch, meaning that it should be periodic, then the way that you build that signal is you sum up harmonics. And that's one of the reasons that wavetable synthesis is so powerful and effective, is that's exactly what it does. It stores harmonics in a table and produces a periodic result. So let's add some more terminology. I want to talk about this term sound event. All right, so in traditional music, we talk about notes as kind of the basic sounds. And notes have pitch, time, duration, loudness, and lots of other properties that get swept into this term of timbre, timbre. Okay, but that's a note. So in contemporary music, the concept of note is a little dated. It's got a lot of traditional baggage around it, like traditional harmony and scales and so on. And modern composers are always trying to break with tradition, and especially computer music people are trying to free up all of the constraints of the past. And so we don't really like the term note because it brings in all this traditional baggage. And so the replacement term for note is sound event. Sound events may be unpitched. They could be percussion. They could be complex sounds like a train going by is a sound event. But sound events do have time and duration and loudness, and of course many, many other possible evolving qualities. So in this course, I will try to refer to things as sound events because I want to emphasize that this is a very general concept. But a lot of times, just because note is such a clean, clear, short word, we'll probably use that term as well. So whenever I say note, just mentally remind yourself that we're not talking about traditional notes. We're really talking about sound in full generality.